welcome back to new topic for this part 2, isomerism. So what we have, let's recall back what we have learned in part 1. So in part 1, I have introduced to you the types of important isomerism that we have. We have 2 important isomerism. And also we have learned about the constitutional or structural isomerism. For this part, we are going to continue with the what we call geometric or cis-trans isomerism. So this is what we have learned in part 1. So where we discuss about the coordination isomers and also the linkage isomers. So in this part 2, we will discuss about the geometric and also what we call cis-trans or diastereoisomers based on the different spatial arrangement. And then here, what is stereoisomer? So stereoisomers are actually compounds that are made up of the same types and also number of atoms that bonded together in the same sequence but with different spatial arrangement. So in this part, we discuss about geometric isomers, or you can call it as cis-trans isomers or diastereoisomers. So, what are the geometric isomers? They are actually stereoisomers that cannot be interconverted without breaking a chemical bond. So, in these geometric isomers, we have cis here, and also trans. So, this is one example for the cis. This is the platinum, or what we call cisplatin. So this is actually what we call cisplatin, and this is almost similar to this one. This is where we have the trans. So the diastereoisomers or geometric or cis-trans isomers, they have what we call the same connections among atoms, but different spatial orientation or different space orientation of the metal ligand bonds. So for the geometric, we have 2 types of isomers, cis isomers and also trans isomers. For the cis isomers, they have identical ligand. They have identical ligand in adjacent corners of a square, and then we have trans isomers where they have identical ligands across the corners from each other. So for the cis, they have similar or identical ligands at the same site, while for the trans isomers, they have identical or similar ligands opposite to each other. For example, here we have platinum complex here. Okay, so it can exist as cis and also trans isomers. From here, this is the cis, where they have, we have here similar or identical ligands at the same site for amine and also chloride. And then for the trans, we have atoms or ligands that are actually on the opposite sides. For example, here we have amine or ammonia here at the opposite side, and then the chloride also opposite side here. So if we have the same side, this is cis. If you have atoms or ligands at the opposite sides, we call it as trans isomers. Another example here, we have cobalt cation or cobalt complex ion. Here we have cis, where we have the same side of ligand here, and then we have trans, where we have opposite side of the ligands. So in this case, for the cisplatin or the platinum complex here, This is where we have in terms of square planar geometry. While for the cobalt here, this is where we have the octahedral geometry. Other than that, these geometrical isomers, they have different ligand to metal ligand bond angles, or what we call LML. So common example here is the cis-trans isomerism. Both actually occurs in square planar and also octahedral complexes. As I have shown to you before this, we have a square planar for platinum complexes and cobalt complexes for octahedral geometry. For example, here I have a square planar, also cis-platin, cis and also trans isomer. Whereas here, for the angles, for the ligand to metal ligand bond angles, for cis, it has 90-degree angle. For this is amine or ammonia, NH3. The angle between here and also metal and also the ligand here is 90-degree. While for the trans, for example, let's take the same ligand, ammonia, NH3, ligand to metal to ligand, it has 180-degree for trans. Other than that, we have here the cobalt complex or cobalt complexes here. This is where we have the cis because we have same side of chloride, and then this is where we have the trans, where we have the opposite side of the ligand here. So this is what we call the cis and also trans. And for the cis, okay, for the cobalt, it actually exists as pink compound, while for the trans, it's actually in green color. So just because the formation or the arrangement or placement of the chloride here, it will give different colors and also different properties. And then I have a question here. Are these additional geometric isomers of these cobalt complexes? So what is the answer? Is it this one can be considered as cis? Or and then is this can be considered as trans? The answer is yes. They are similar to each other. Just because the arrangement is a little bit different, but in this case, these chloride are actually in the same side, and then also in the same side here. So both are similar. And then we have trans, the chloride here and also here, and then also same with here and also here. And it can be here, let's say chloride here and also chloride here. They are both the same. And then I have one example here. We have cis-trans isomers in octahedral complexes. Usually cobalt complexes, octahedral. So means here the coordination number is equal to 6. And then we have dichloro, because we have 2 chloride here, dichloro bis ethylene diamine because we have 2 bidentate, and then cobalt 3. Please make sure that we don't have any space between cobalt and also number 3 here. No space at all. So for example here I have cobalt for cis isomer. The color is purple, while for the trans isomer, the color is green. So the orientation or arrangement of these ligands actually affect the physical properties of the compound. That's the last slide for this part 2. I hope to see you guys in part 3. So please don't forget to like, comment and also subscribe. See you guys in part 3. Bye!